Okay. Hello, everyone. Thank you for joining GeoScience and GeoEnergy webinar of 9th of July 2020 today. It is our pleasure for us, Sebastian Geiger from Heriot-Watt University and myself from TU Delft to host you all in these webinar series. We are especially grateful to our keynote speakers who have supported this initiative and to you all for joining us and combat work from home isolation. Please subscribe to our YouTube channel and help us spread the word. All previous lectures are available on our YouTube channel. If you subscribe to our channel also, you will see the upcoming talks as well. To our student attendees, please attend also Poros Media Tea Time Talk series to share your research and broaden your professional network. Now to the lecture of this week. We are pleased and honored to announce our keynote speaker of this week is Professor Mark Bentley. Mark graduated from the University of Wales in Aberystwyth with a PhD. Mark, I hope I pronounced it well. With a PhD in structural geology. He then joined Shell as a petroleum engineer, worked on and offshore, both in the UK, then had a spell in Oman, and finally Shell Research in the Netherlands, where I am speaking, working on the application of reservoir modeling technologies. He used to live also in Delft. Speaking to you all from Delft, it makes me wonder why he left this nice city. He then left Shell to join Trax, a small Aberdeen-based consultancy offering training and consultancy to the industry. From his career trajectory, Mark clearly likes to travel and see the world. And you know what, this also quite resonates with many of us in academic environment. It reminds me of Hans Christian Andersen's quote, "To travel is to live." He has aimed to run events on every continent. The first 6 came reasonably quickly, but Antarctica is proving to be a challenge for him since penguins generally are uninterested in reservoir modeling. So Mark is working very hard to see if that can be also resolved. In addition to training with Trax, he now also works at Heriot-Watt University as a professor, where he took up a chair in mature field management since 2018. He has previously been a distinguished lecturer for the SPE and EAGE, European Association for Geoscientists and Engineers, has twice been awarded the Bonarelli Award by the EAGE and is co-author of the reference textbook Reservoir Model Design, the second edition of which is he has fully expected to complete during the lockdown, and he's still working on it. I guess that's the positive side of this stay from home. So Mark, I hope you're making your promise honored. It's our pleasure and honor to host you, Mark. Thank you for making the time and for your care for the well-being of the society as well. To the audience, please note that Mark's lecture will last for about 30 to 35 minutes and then followed by questions and discussions. Like before, please write in the chat room your questions, text them, and Sebastian will go through them and share the discussion session. Also, you don't have to wait until the end of the talk. If you think that there is an appropriate time to write your text, please do write your question. Many thanks, Mark. Once more, the stage is yours.
Okay, well, thank you, Hadi. Thank you for that kind introduction. And yes, we should finish the second edition, but there's always more things to do like this during the lockdown, so it can always be put off till tomorrow. I'm guessing in the groups, the assembled group today, there's plenty of us who've done reservoir models or simulation models over the years, and I think hopefully it's a familiar theme to you that after a while doing this, you do begin to wonder, are we actually making good models or bad models? And that's the theme of today. And I'm going to show you 4 models here. These are ones I've made in recent years, so long enough ago that we can look back on them and consider, were these any good? And I'm looking at these 4 models. 3 of them, actually, they did help us to get to a decision point. They were reasonable pieces of work. They made a contribution. One of them, actually, in hindsight, is pretty much a complete waste of time. Impossible to tell which one just by looking at them. And I think herein lies the problem. The software wouldn't declare that any of these is not okay. That's not the job of the software. That's our job. And for most of us in the business, especially those who haven't made the models, the way we meet models is rather like this. We meet them on other people's PowerPoint presentations, where, to be honest, we have no real way of telling whether they're good or bad, or it's hard to tell. And that's the dilemma. Sometimes we build good models and sometimes we build bad models. And of course, what we want to do is use our time usefully and make good ones. So this talk is about how can we distinguish, what can we use as guiding principles? And again, in the audience, in the group, I'm sure there's all sorts of ideas on this. For what it's worth, I'll kick things off with mine. Thoughts on what makes the difference between good and bad. And I'll start with bad. And when I say bad, I'm going to speak with the authority of someone who I believe I've made all of these mistakes. So I'm referring to my own past in this respect. And a couple of things where I think they tend to be roads to unhappiness. It's the meaning of the model. And I'm putting up here a model. This isn't one of mine. It's one I found it on the internet. So if this is made by anyone in the group today, by the way, firstly, let me know. And then at least I know who I got it from. And then the second one, my apologies. Actually, this is a reasonably effortful attempt to make a picture of what it really looks like down there. It's a stack channel sequence. If you look carefully, actually, there's this. I don't underestimate the amount of time this must have taken to make. There's the representation of bar forms here. There's sort of an active channel fill, and everything's nicely stacked up. And this is an attempt to model reality. It's an attempt to make a model of what it actually looks like down there. But is it a good model? And I would have to say, without knowing the reasons why this one was built, if the reason was to go to flow modeling, I'd have to say, actually, no, this is not a good model. If there's any reservoir engineers listening in today, have a look at the cell sizes, these cell shapes. These do not go very well in a finite difference simulator. To get this to converge and to run, probably the reservoir engineer will have to blank out a lot of the cells. That'll change the connectivity. And long before then, if you think about the 3D petrophysics and the geostatistical part, I mean, that's done according to cell stratigraphy. Well, where is the cell stratigraphy? And to be honest, by the time you've got this cellular configuration, the cell referencing is pretty much shot. So no, this, to be honest, is not really a good model if the purpose is to make it flow. The picture at the bottom, this is also a channelized sequence. It doesn't look like it, but I would suggest that this is actually quite a good model. Not because it looks like reality, but because it represents reality. And the reason I like it, and I guess there's a bit of bias because I made it, but it's because it relates to this sketch here. So this is reality. This is a sketch of an outcrop. This is one bed, and the model at the bottom is a model representation, and it has the elements have been chosen to be contrasting. Their sizes are represented. That's all in here. The length scale of the property variation with the elements is in here. The connectivity is right. It's a representation. It's a reasonable representation. It's a model, and I think somehow we have to release ourselves from the thought that we're actually trying to make a 3D model of what it actually looks like down there, because we just can't. It's too complicated, and we don't need to. And the clue is in the word model. We tend to assume we need to represent or to recreate what's down there, but we don't. We just need to make a model representation, and a model doesn't mean you're going to make something exactly that looks the same. So once you've got into that idea, we're immediately in a better place. The other one is complexity, and I owe a debt here to Phil England, and apologies if you've seen this stuff. I've taken it to a couple of conferences. It's my favorite quote of the last couple of years. Phil England and I, we were sitting next to each other at a conference, and we got talking about modeling. He had similar prejudices to me, and he came up with this, which I thought was great. He said, it's a philosophical point. We have a complex problem, and we tend to assume that we then need to build a complex model. Otherwise, we can't capture the complex problem. And at first pass, that seems okay. So we go on and we do it, and we end up with a complex model. And the problem is, it gets too complex. And there become a lot of parameters in there which are convolved, and they start interacting. It begins to get difficult to see the wood for the trees. Moreover, these things take a bit of time to build. And I think the life cycle of a model is often longer than the life cycle of the person doing the job in that job. You know, we move on. And sometimes the models just stay there longer till it's almost like they become another member of staff. You know, you ask people where to drill a well, and we say, well, let's talk to the model, as if it's a staff member. And when that happens, models pass hand to hand, and it can come to the point where no one has particular ownership. and it becomes difficult to work out actually why some of the things are in there that are in there. So what happens is you start off with one thing you didn't understand, the problem, and after a lot of effort and time, you end up with two. You have a complex model which nobody really understands, and then of course you've got the original problem, which you're nowhere closer to solving. This is the worst case scenario for modeling. This is not what it was all supposed to be about. Neither are we supposed to make models what it actually looks like, because we can't. And neither were we supposed to necessarily make it overly complex. It's a model, the clue's in the name. So if that's bad, well, what's good? And I'm going to put things in 4 categories here. And for those of you who have been on the modeling classes, this is going to be repetition. Actually, if any of you have been on the modeling classes and this is completely new, then I'm obviously not a very good tutor. So here's a bit of catch up. The first one is concept-based modeling, and this is the well-used quote: "If you can sketch it, you can model it." The second one is fluidcentric design, which is all about Flora and Darcy. The third one is scale, as distinct from upscaling, and there's quite a big difference between the two, and I'll come to that. And the evergreen one is uncertainty. And the thing over the last couple of years, and this probably wasn't in the modeling class for those of you who've come to them over the years, for the last year or two, I've been struck by what happens when you do some modeling and all it shows you is that you really don't know. Where do you go? And I'm going to finish on that point. So 4 things to count us down through the session, and I've got things which I initially intended to be Olympic rings, but having done it, I now realize that's something completely else, and that's a tribute to the marketing of vehicles, clearly. Anyway, we'll count down 1, 2, 3, 4. So if you drift off halfway through, just have a look on the top right. When we get to 4, we're at the end. Number 1, concept-based modeling. What's this about? Well, we work in a situation of data insufficiency. And what that means, it means we can't expect the software to come up with a reasonable model just based on the absolute data we give it. We need an underlying concept. And the question is, what do we use as a concept? And for talks in companies these days, and it's the same at the university, you see a lot of this. Google Earth. Google Earth is a miracle. It's a wonderful thing. And I don't think we should stop using these sort of images because it does brighten up an otherwise dull presentation. But they're not great for model design. It's a modern day surface for a start. This is how sediments are collecting, not how they're preserved. And of course, it's 2-dimensional. So yes, use them because they are beautiful, like this image here from Oman. But much more useful is a concept like this. So we have the picture of the outcrop, and we're over there in Utah. But more importantly, it's the sketch. It's the concept sketch. And I would argue that anyone in a reservoir model should be guided by some kind of concept sketch. Now, why? Well, unlike Google Earth or a photo of the favorite outcrop, that sketch at the bottom is highly interpretive. Someone's chosen to break it down into a certain number of elements. They have a certain degree of connectivity. This is a concept sketch of how the reservoir has been preserved. And actually, a skilled reservoir engineer, when you add some properties on these colors, you can tell a lot about how this field's going to produce just by looking at the architecture. This is a useful start to reservoir modeling. If you can sketch it, you can model it. If you can't sketch it, what's happening in the modeling software? Well, probably a series of defaults and a certain amount of making it up as you go along. And this is why some of the most exciting developments in software at the moment are Sketchbased. It's why when we go to the outcrops, and here we are in beautiful Barrowfundle Bay, which is not far from here. There's the group working away. There's Maggie, obviously working too hard, having a bit of a nap there. Everyone else is working quite hard there. What we're doing, we're building a sketch, and we go there and we look at what's inside the rock there, which in this case is a rather complicated carbonate. And then we have a look at these, which of course are the fractures on top of it. And we take those two together, we get out our pens and pencils and we start sketching. And that's my sketch, a multi-scale sketch of that outcrop, just based on walking around it for an hour or two and then looking at a thin section of some limestone. Now with that, we can log on and make a model. There is no chance or no reasonable chance that a piece of software unguided will come up with that sketch just from the data. Yeah, we need to sketch it first. Hence my enthusiasm for this. You may have seen this before. This is actually getting on for Olsen et al. That was 2008, wasn't it? And this is a good 5 years or 6 years old. You may have seen this. This is Matt and co, Matt Jackson and co at Imperial, and there's quite a lot of et als there. And it's Sebastian and some et als there at Heriot-Watt, and then Mario Costa at the Calgary and others. And what they've been working on is sketch-based modeling. So this is the ultimate thing of linking your sketch to the model. You literally sketch it. So this is sketching it with a pen on a pad. And this is a few years old, but if I take us back to the relatively recent, oh yes, Mario, he used to work at Pixar. I mean, this is the point, and Matt makes this point as well. If you surface-based modeling generates Buzz Lightyear. If you can do Buzz Lightyear, you can definitely do a channel. I mean, it is relatively simple compared to producing something like that. The technology is there. It's just not been fully mapped into our lives in oil and gas, although Matt and Sebastian, Mario and others are working on it. So that's turned into RRM, Rapid Reservoir Modeling. And just to show you that we can use it, this is last year. This is Stephanie and Ava, who are MSc students at Heriot-Watt. And we're down here. This is the Cornish Geothermal Project. This was their project, was to model this up. And what Stephanie is there is holding Microsoft Surface, and she's got a pencil on the surface, and it's starting to sketch that outcrop. And that outcrop is full of fractures. There's a major fracture zone running through there, and we're unraveling the architecture. So a day in Cornwall doing that, you can do it. And I'm guessing Stephanie might be on, in which case she would tell you that actually, it's research software, so it kept crashing. I'm sure that's going to be fixed. Actually, the main problem there, it was so sunny for that day that you couldn't see the screen. But you can fix that by retiring to somewhere where it's not sunny, get yourself some brown Coca-Cola, and still with the pen, just finish off the model. If you can sketch it, you can model it. You then attach it to the flow diagnostics, in this case, Victoria Spooner on the left, one of Sebastian's and Dan's students at Heriot-Watt, wrote the flow diagnostics from this. You press return, and that sketch turns into that model, and then you get the effective properties of that sketch. And as long as everything doesn't crash, it all works quite quickly. And you compare that to other ways of doing a fracture zone, using something like a DFN, which is still too stochastic for my liking, I have to say, but that's sort of the standard type tools. Which one's better? Which is the better model? I've got to say it's the one on the left. And the reason that I think it's better is because it's hardwired deterministically into an underlying concept. You get a concept, you sketch it, you model it very quickly, you get the properties, you're done. It's a model. Number 2. Fluidcentric design. This is Flora and Darcy. So if you've got your sketch, the question now is, how much detail do I put into that sketch? And that takes me to the right back to that first slide. Which of these models was the one that was not good? Well, it was this one. It's actually quite a pretty model. I was assured by the sedimentologist who I was working with, a very good sedimentologist, he swore to me that these channels really were like wiggly worms. So fair enough, he knew more about it than I do. He had 3 types of worm. We had overbank stuff going on here. There was heterogeneity within inside the worm. And this took a little while to make, and it sort of seemed to be very elegant. The only problem really, I think, is just a complete waste of time. Why? Well, it's a gas field. And all we really need to know is how much sand is there and how well connected is the sand. We don't really need to know what color the wiggly worm is. So I've gone into way too much detail. It's overly sensitive. It's much more sensitive than the fluid. And this takes us to Flora, and I'll spare you Flora. There's a story here. If you've been on the course, you know the story of Flora. But Flora was someone who used to work with at Shell, and who pointed out to me that the amount of detail I put in the model isn't actually to do with the geology. It relates to the geology, but it's not to do with the geology. And as a geologist, that hadn't occurred to me. And she pointed out, as a petroleum engineer, in fact, a reservoir engineer, she said, actually, it has to do with the fluid type, mostly the viscosity and the production mechanism. And there's a rate dependency in there as well. It relates to the geology, but we're not fundamentally making geological models. And that had not occurred to me. When we're doing peer reviews and people start talking about the geological model, I think that's the time to get nervous. These are reservoir models. They are reservoir models of flow, subsurface energy systems. We are just modeling a subsurface energy system and how it flows. Relates to the geology, but it's not a geological model as such. Geological model is something in your head or something the explorationists have when they're doing play concepts. This is different. This is petroleum engineering. So the rule of thumb, and this is Flora's rule, which she taught me, single most useful thing I've been taught in my whole career, actually. And she said, look, you need to look at the order of magnitude permeability contrasts. So here we have a K-phi plot from core plugs with a nice scatter on it. You said, look, spectrum of complexity, fluid types from dry gas through to heavy oil, and a spectrum of production mechanisms from depletion through to the sort of EOR type things at the other end, the difficult end of the spectrum here. And depending on where you are on that spectrum is controlling the amount of detail we need. And the rule of thumb, because it was nice and quantitative, was to look at per porosity class, look at the scatter on you got here, and then say, okay, if this is a gas field, you need 3 orders of scatter until the fluid is sensitive to the heterogeneity. Bear in mind, we can relate this cluster to a single line, so that we still get a variation in permeability following porosity. The question is to what extent do we start splitting up the data set? So Flora's guidance was that you need 3 orders of magnitude if it's a dry gas. If you're in the middle here, an oil field under depletion, you tend to be sensitive to 2 orders. And when it's EOR, then we pick up the 1 order contrasts. So over here for this cloud, you could just about get away with modeling that as with a single relationship there and model it all as one type of sand. And that's what I should have done with that last model I showed you. If it had been a heavy oil system, different case. We should then start splitting things out. But it hadn't occurred to me to take this fluid eye view of the reservoir. I was looking at it as a geologist, not as the fluid. We need to think like the fluid. The other thing we need to think about is scale, length scale. So once we've got our fluid type sorted, there's the length scale of the heterogeneity, and which I think is something we're all familiar with. And then there's a slightly more abstract concept of the length scale of the development question at hand. Just to pause on that, if you think about it, and it took me a while to come around to this, but everything we do in the subsurface, all of our developments, and it can be anything. This is not oil and gas. It's the same for geothermal. It's the same for CO2 storage. You've had Phil Ringrose already talking about that. All of those questions or activities have an implicit scale, and very often it's the distance between the wells, and that's what we need to compare with the length scale of our heterogeneity. And once we've got that and a Flora's rule, we can make a nice little flow chart, and I'll give this one to you now, which can guide us into how much heterogeneity we put in this model. How much detail do we put into our sketch? Where do we stop? And if you follow me down here, this is, of course, we have to observe everything. It's just that we don't use everything that we observe, or we don't stuff it in the model just because the software allows us to, and because our computer's big enough. We need to put in the amount the fluid will be sensitive to. So if the heterogeneity is not significant according to Flora's rule, we don't have to worry about it. If it is, though, then it's a question of length scales, and we're in one of 2 situations. Either it's like this, so heterogeneous it's homogeneous, or it's like this, much bigger length scales. You've got some spatial continuity. Compare the 2 length scales, and then that tells us what to do. So on the right, the heterogeneity is still important, but we can catch this with some very well understood and well-practiced averages. On the left, well, that we have to model. And that, to go back to our early years, that's why we started doing modeling in the first place. It's quite hard to come up with an average for that because it's not a repeating pattern. So we do our sketch. We need to be concept-driven, but it has to be a fluid-sensitive sketch. Only model it if the fluid can see it. Think like the molecule. Let's not think like geologists. Number 3. Scale rather than upscaling. Why rather than upscaling? Well, this gets us to mature field decisions, and I'm sort of hoping maybe Caroline Hearn is out there somewhere. Got a project we're trying to get going at the moment, the land of lost heterogeneity. Most fields are mature these days, and that's why at Heriot-Watt with the new MSc program is, actually the new one is subsurface energy systems, the future, carbon transition, but the new one 2 years ago was mature field management. Most of our fields are mature, and with mature fields, we are sensitive to the finer end of the heterogeneity spectrum because we're looking for the last 10% or 5% or maybe 1%. And it turns out that no matter how big and complex our model is, and no matter how big our computer is and the rest of it, we are still missing heterogeneity because we're trying to catch everything on one scale, and we just can't do it. I mean, there's a tendency to say, if you think where our modeling starts, where does it start? You go to the poor old petrophysicist and say, have you finished with your logs yet? Can I have the last file? And you load the last file and you say goodbye to the petrophysicist. And then you think, right, if I can just get all this in my model, that'd be a pretty good model because this is pretty detailed. But no, not really. We need to remind ourselves here, and this is down here in Pembrokeshire, again, on one of the courses. This is the shower curtain, the thing that Maggie and I lovingly carry around the world. And it's just a reminder of something we all know, which is the volume of investigation of the standard logging tools. Now, of course, you do a lot better with image logs. If you have them in every well, then good. But if you're not in Saudi Aramco. You probably don't do that. So you have to use standard open hole tools, and they are averaging. They are quite lazy. And when you plot a log on real scale, and here we are down on the beach in Barrafundle Bay looking at a log plotted 1-to-1, it's quite good for the soul to do this, because then you realize, you're reminded that this really is a moving average, and that's Phil Ringrose on the right. And as you can see, he is unimpressed by the laziness of that log. So if we have fine heterogeneity in there, then basically we've lost it. Now, this is how models can very easily go bad. And I've done plenty of this over the years, hopefully less these days. But it happens like this. Let me give you this in 6 steps. How models go bad. If you have thin beds, so deep marine systems with low net to gross, this is where it really begins to show, because you can have a lot of it that looks like this. Well, through this interval here, there's maybe only one of these beds that you're actually capturing properly with the logs. Because not because the logs are bad, it's just they're taking very accurate moving averages, which gives us an interesting number, but not the number we need, which is the number within each bed. So what do? Load the LAS file. We take that, step 2, and then we block the logs, and we play around with the blocking. And we spend a lot of time here often to get these things the same, because these are these diagrams where we look at the ranges spread on our original log data, and then on our upscale data, and then on our model. And we try to get them the same. And we take them to peer reviews, and if they're close enough, we pass. Well, if it's the wrong number, then what we've done is spend a long time ensuring that that wrong number is faithfully represented in the model. We take that wrong number. We then pick up some core plug data. That's measured at a different scale, and we assume it doesn't matter. It does, usually, but let's assume it doesn't. And then you go in with this wrong number into a cross plot, which is actually a bit of a cloud, which someone's shamelessly put a line through the middle of. And we go in with this wrong number, assumed it's the same as that wrong number, go into a cloud that's ill-defined and come out with a permeability. And we're on our way now. It's not a meaningless number, but we're on the path. Step 4, we then put it in a cell and assume that that cell is homogeneous and that that wrong number will be appropriate over something the size of a hockey pitch, soccer pitch if it's a big field, or maybe a basketball pitch, a big pitch basically. And then we combine it with a prosody. And do we use this one? No, we go back to this one, which was wrong at this scale. Why? Because we've already got this through the peer assist, and we're not going through that again. So we carry on, and we say, okay, the reservoir engineer will sort this out. We pass it to the reservoir engineer. We go up in scale a little bit to the reservoir engineer, who then finds it doesn't match the production data. And then the reservoir engineer has a choice. And on the whole, I've found reservoir engineers over the years to be very reasonable, practical people. And they can go 2 ways. Either they go back to the geologist and start the whole process again. But if you've been waiting for 3 months to get the model in the first place, and they've only left you 2 weeks of the project to finish, you're probably not inclined to do that. And you will start doing things, multiplying things. And the fact you've got a wrong model, you do something else wrong in the simulator, and you hope that 2 wrongs equals a right. And then you make a forecast, which by this stage is pretty meaningless. And we use that as the basis for making a multi-million-dollar decision. Okay, this is a bad day at the office. It's not always this bad, but just look out for the word heterolithic. If you have that word, this is probably happening. The other word to look out for, of course, is limestone. This happens very commonly. And we remind ourselves that by going out in the field. And here we are in the field, and this is a long time ago. This is in the bad old days, or the good old days. 2019, as we used to call it. This is just literally a year ago. And we're down there. Many of you, if you've been out in the field, will recognize this. Above our heads, pretty impressive, fairly homogeneous sandstone. And what you need to do is get a sense of scale. Good to take a friend. That's John Howell, Aberdeen University. And he allows us with his, he has a drone. Always bring a friend with a drone, because it allows you to do something which you definitely can't do at this location, which is step backwards. And you can step back, back, and back. And it turns out there's a nice big sandstone underneath us as well. And you can throw a grid on that. In fact, those cells are probably too large. Make a simulation model and you're away and you're done. But are you? Well, no, let's go back in, back in, back in. The reason there's a path there, albeit perhaps not quite wide enough, is because right behind us, and you can see it behind me there on the left, is a heterolithic. And the permeability is not 0. It's a number that's hard to guess and that you can't get from a wireline logging tool unless you've got an image log. And although it's volumetrically minor in terms of its impact on flow, and many people have looked over this over years, Pat Corbett, Carl Stevens, all these kind of guys at Heriot-Watt and many others in Imperial and other universities, Delft, the Delft group will have looked at this, many others. We know that these things have an enormous impact on flow. Do we get the numbers right? Not using the standard workflow. We need to get ourselves down to the scale of data, and that's why the last couple of conferences I've been to, we've been showing this stuff. We've been calling them, rather ambitiously calling them truth models. The idea, these are models we weren't able to make before because we didn't have the computing power. So the idea here is to resolve these at the scale of the data, but model at the scale of the question. At the scale of the data is a core plug. So the grid cells need to be the same size as a core plug. So the data goes right in on scale, but you model at the scale of the question, which is often something like the well spacing. So if you just have a look at that little bed down there, that nice white polished bed here at Swan Lake Bay, also down here in Wales. This is where we run the modeling class, by the way. That's why so many pictures of Wales, apart from being God's own country. If you just take that one bed and then make a sketch and make a model, and I thank Rona Hutton and Tom Buckle for actually making this model. I've got an addendum to that. If you can sketch it, you can model it. When you're at a university, if you can sketch it, you can actually get someone else to model it. It's great. So thank you for Tom and Rona for doing this. And they've used multi-point statistics and made a very nice representation of my sketch. And then Ed Stevens at Tracks has then made some simulation models. It's only 4 meters high, 400 meters long. It's a 2D model, but with cells the size of a core plug, there's 3 million cells in here. So all the physics is switched on, and there's no apology here for the physics. Everything's on, hysteresis, the lot. And what you get is models. I've never seen models like this before on this particular scale. It's showing you what it would look like when you're flooding through that bed. Absolutely quite beautiful models, actually. And then you begin to play with things like, what's the viscous force doing? What's the gravity force doing? And then what happens if I turn hysteresis back on? Because it often gets turned off to improve run times. Turn it back on, and you can see what it's doing. And it's giving us these 10 or 20% differences. And in mature fields, that can be all the difference. And I'll show this one. This is Ed Stevens again. This is one this year on EOR. This is WAG. And same bed, water, gas, water, gas, water. And what it's illustrating, well, what it's illustrating is that it's not a good process for flooding this bed. This is a highly inefficient WAG. But you can see it. And these are models for understanding on scale, on the scale of the data, but at the scale of the question. And fortunately, we can do that now with the computing capacity that's available to us, not by making full field models that are a bit more detailed, but by changing the scale at which we model. There's no upscaling here, but we're changing the scale at which we're modeling. 4, nearly there. Uncertainty, what to do when you know you don't know. Well, lots of talks of uncertainty over the years. It's the perennial issue, isn't it? I think I've shown this a few times. We're all basically in one of 3 camps. There's the best guessers at the top, making a single model. There's the multiple stochastic groups down here, and there's the multiple deterministic people here. But it is a triangle. You can blend these. You can blend these. These are extreme end member cases, but you can blend these. Where's a good place to be? Well, over the years, the argument has been, a best guess model for a multi-million-dollar decision. I mean, really, it has to be a very special circumstance just to make one model. I do think it's fundamentally flawed. I've got a preference for scenarios, multiple deterministic scenarios, but things like low, mid, high case modeling, to be honest, that's not that different to a best guess. Otherwise, which one do you make first, the low, the mid, or the high? Probably the mid. Then you do the low and the high, and then you average, or take one case for reference. Which one do you take? The mid. Well, that's the one you started with. Really, this is just base case modeling with a quick sensitivity. That's not really uncertainty handling, so it sits up there. Where we need to be pretty much all the time is down the bottom here, somewhere with some combination of stochastics, multi-stochastics or multi-deterministics. Now, in terms of where you should be, I mean, I like scenarios still. Very interesting. Ensembles, very fashionable at the moment. The jury is out to some extent about whether it's really helping or not. There's certainly some good things you can do. And my colleagues, Dan Arnold and Vasily Demanyov and their group at Heriot-Watt, they're working at this. There are some interesting things to do. To be honest, I think you can get the right answer either way. You need to not be up here at the top. What I want to focus on today, just as my finishing point though, is what happens if you do this really well. And I'm going to take an ensemble, and here it is. It's a redraw based on a real piece of work by a group who actually did a really, really good job. I mean, they really listed out their uncertainties. They really thought it through. They modeled them faithfully. They were good models, and they came up with this. So on the x-axis, time; on the y-axis, cumulative production. And my thought is, well, what have we actually shown here? What we've shown, or what is shown here, is that it could be quite a good outcome here, but could be very bad, or it could be in between. And that's pretty much it. So what we're really showing here is that what we now know is that we definitely don't know. And you could go further with this and do clustering and break out one or two cases, but actually I think this is the point to stop, because this is the point where we're revealing what we know, which in this case is that we don't know. So pulling out a couple of preferred cases here, I'd suggest, is actually not a good thing. We need to stop at this point, look at this range and say, well, where are we relative to that multi-million dollar decision that's about to be made? And I would argue that actually we stop at that point. And this is the thought from the last couple of years. So I'm going to finish on this one. One of the nice things about being associated with the university is that if you're lucky, on a good day, you can bump into someone in the corridor and have an astonishingly insightful conversation. It happens in business as well, but it does tend to happen more at universities. Especially if you bump into someone like Dan Arnold, who you might know. And I think every conversation with Dan is precious, because by the end of it, you've generally moved on or come up with some ideas. And we were talking about this last year, and we ended up thinking, yeah, well, through this whole thing of modeling, we've never really questioned the assumption that there's some kind of problem and that we're trying to find some kind of solution. And we're using modeling and simulation to get from the problem to the solution. The picture I just showed you is that we weren't converging on a solution. So we can't do that. But it's right that we're not converging on a solution. That's what the models are telling us. So what do we do? Well, I think all you do is swap out the words. So instead of problem, we say question. Instead of solution, we say decision. And it's a revamp of this decision-led modeling, which was fashionable for a while, a decade or so ago. But I think that's the way I think that's a good way to go. We will always have questions, and for sure, there's always got to be decisions. There doesn't have to be absolute solutions, but there will always be decisions, in which case modeling and simulation is there for understanding. And now we can begin to map what we do onto this space. We've abandoned the idea of trying to recreate a picture of what it really is like down there, because that's futile. We're abandoning the idea of complexity for the sake of complexity, because it's just too complicated. Let's just look at understanding. In which case, the truth models, they fitted down here quite nicely. And the things that Dan and Vasily and people are working on, like machine learning, well, where does that fit in? There's an idea that machine learning has to do with finding solutions. And I think I'm coming around to the way of thinking that's not right. I think machine learning is a wonderful way of building understanding. And when it comes to things like AI and creative computing, and this is Dan's interest at the moment, and I was asking Dan, where would it go? And he said, and I was half expecting him to say, or find solutions. And he said, no, but I can use it to build some truth models for you. And I thought, yeah, that's good. This is all about building understanding. Now, once you've got the understanding, you could, if you wish, make an ensemble, if that helps. Or you could do scenarios, if that helps. But I've just got the feeling that a lot of the time, if we really did that bottom half of that diagram well, and you generate enough understanding, you may find that through sheer petroleum engineering experience, with the assistance of some models, you can just make the decision anyway. So to close, good models and bad models. What's bad? Well, bad is the attempt to model actually make a picture of what it's like down there, because it's basically futile, and we don't need to. And the second one is just falling into the default of the detailed full field model. Sometimes we need them, usually we don't, but we tend to fall into it, and that was this thing about modeling for comfort. What's good? Well, it's the four things today. I would suggest concept-led modeling, looking at the reservoir like the fluid, not like your favorite piece of geology. It's on-scale modeling, rediscover the lost heterogeneity, and if it's at a very small scale, then simply model at a small scale. Plenty of work in the universities, Imperial, Martin Blunt, all of that, years and years of this. We know how to model a small scale and get the effective properties. We've known that for years, we just tend not to do it. So let's rediscover the lost heterogeneity. And then for model uncertainty, let's use it not to hide what we don't know and to converge on a best guess. Let's use it to expose what we don't know. And once we don't know, I think we're in a lot better situation for decision making. So to finish, sometimes modeling to understand the question, I think, is more important than building big complex models in search of solutions. Whoops. That helps us consider, or it changes the way of what we consider to be good. Thank you very much.
Okay, so thank you very much, Mark, for the very nice talk. I already see plenty questions are being texted, and we would expect also more to come. So I'm going to hand over to Sebastian to chair the discussion session and put myself in mute.
Thank you very much, Mark, for a great talk. Yeah, plenty of questions. I start with something very easy from Mohamed Rawai. He said, where's that big outcrop? And Anna Clark said she believes it's in Greater Dano in France. Is that correct?
Yes, Anna knows it very well. So it's the scaff rails. So thank you to Stan Stanbrook, if he's out there, for showing me the scaff rails above our town.
So coming to a more challenging question from Mohamed Rawai, how do we know that we have reached the right enough balance between the finite model and the infinite Mother Nature? So what is the appropriate scale? How do we know what scale is good?
How do we know what scale is good? Well, I think we ask the fluid. So we ask the fluid what it's sensitive to, and then we look to the length scale of the heterogeneities that the fluid is sensitive to. So ask the fluid, I think, is the answer. And because it is the problem, otherwise you can go on forever with these models. So think of it like the fluid and try and imagine what the fluid would see and model on that scale. And that's where it stops. We're not interested. It's a subsurface energy systems that we're modeling. Just see it like the fluid.
And Mohamed also said, no, thank you very much for the talk. Sticking with scale, and I'm just sort of jumping between and trying to group questions as they come in. Fluent Doster asked, thank you, Mark. When you have taken the question of scale to the data, how do you bring it to the scale of interest?
Well, the scale of interest, it comes down to model purpose. So the scale of interest really is it's this thing about what are we modeling for, Florian? We must be modeling to answer some kind of question, and that question will invariably have a length scale. So it is that thing of it's the thing of designing a piece of model, a model workflow which gets us from the scale of the heterogeneity that the fluid sees to the scale of the question that's being asked, which is very often the well spacing, and then we're into multi-scale modeling and effective property modeling, which again is something very well established from the 90s, really, well earlier probably. The key thing is framing. This is all about model framing. I think there must someone somewhere must be asking a question, and that question has an implicit scale. And once we know that, relatively easy to find out the scale of the heterogeneity, fluid sensitive, and then we've bracketed the part of infinity. I like the way you say that, the part of infinity that we're interested in. Is that a good answer? Sorry, just give me a thumbs up on it.
Mispronounce the names. As a question, Mark, thank you for the presentation. Should we build models always based on rock types instead of facies, since we can characterize better the flow and fluid flow and heterogeneity?
Well, completely, absolutely. And yes, no, don't be limited. Facies is one of these things that geologists get excited about. So that's part of building a mental concept. And but no, when we step into the model, we then have to choose. We quite like to use the phrase model elements, just because it avoids the word facies. And you don't always need to take all the different rock types in. I think rock typing usually gives us more categories of rock type than we need. I think it's a good thing. But then we need to lump them together. So it's the same thing. We look at we do the rock typing, then we go back to the fluid, and we go back to flora, which is really Darcy, and say which of those rock types really is distinct enough in the context of our fluid, and then we can start combining the rock types, and it will come down to the number of elements that we then take into the model. And I mean, Sebastian, you'll be very familiar with this with carbonates. I mean, carbonates are a devil for rock typing, taking you to 20 different rock types. But a lot of them are actually fairly subtly different. And there's a truism, which I think a lot of reservoir modelers come up with after the years, that there's a strong tendency to have the good, the bad, and the ugly, and end up with 3 or 4. And that's often the case. And it's basically because of those levels of the orders of magnitude contrast. And our systems typically have 3, 4, if we like, at the most 5 orders of contrast. So you do tend to end up with the good, the bad, and the ugly. Sebastian, by the way, do we leave the screen on, or do we go back to faces?
We are back to faces, so you can I've already taken care of that, so we can see your mark. We have a question from Petro School, and so you never make it right, yet the model can be valid in terms of prediction of the reservoir properties, well performance. So I guess it's more a comment.
Yeah, I mean, it's the old quote from Box, isn't it? All models are wrong, but some are useful. Yeah, I think the thing is that you just have to have more than one model, I think. Don't we? That's the conclusion. Given that sentences like that and then the old quote from Box, isn't it crazy that sometimes we build one model? It's amazing, isn't it? I mean, it's fun. I think it's scientifically flawed. I feel quite strong about that these days. You take a hell of a risk by just making one model and then making a decision on the basis of that. So I agree with the comment.
More comments than perhaps a question from Mohamed Butelja. I think the purpose of modeling is the critical parameter to guide the GeoEnergy and Reservoir team to set up the methodology and the strategy for the modeling workflow.
Yes, it is. It's all about. Yes, I agree, and that's what we call reservoir model design. Absolutely, and you can do that before logging on. I think the trick is to resist the temptation to sit down and switch the computer on, because we feel a lot of comfort sitting behind the workstation, and it's to be honest, it's more of a pain sitting in design meetings with other people who might have differences of opinion. But those first days of sitting together and thrashing it out, and accepting a colleague who will tell you that you're about to do something irrelevant. I mean, we have to be a little bit humble at these framing sessions and accept that, yes, I really wanted to model that channel because I just like them. And that's actually not good enough. And sometimes it takes someone else to point out that you're doing something for fun rather than because it's necessary. But once you have an agreed design, yeah, then we log on a model before we waste time fiddling around.
You should point out there are many comments thanking you for a fantastic presentation, a great presentation, and many familiar faces here, Mark. I'm not going to read through all of them, but lots of positive feedback on your presentations.
I'm on my Christmas card list.
Good. We also have some people, and just as a quick side note, even watching from Malaysia, and I think it's just getting to midnight, so there's some really dedicated people watching from all over the world.
I think it's doing well. Boy, not bad if you don't.
Coming back to some scientific questions, this is a two-part question. So Musa Hosseini Mir asked, with explicit fractures, for example, embedded fracture models, volume of the rock grid cells may be significantly different from fracture grid cells. And he continues, given the noticeable difference between the scale of flow velocities, would you have any recommendations on how to overcome the inconsistency and convergence problems caused by such an issue? So how do we deal with fractures representing fractures in models such that they actually work at the end?
Well, I'll go to the carbonate reservoir modeling research group at Heriot-Watt University and ask Sebastian, because he's got so many research students. One of them will have the answer, and Hadi will have them as well. So I think the general answer, this is an REV question. This is representative elementary volumes, and it was the fracture people who were the best at REVs. The early work on representative volumes was done by them, but for that reason, there's too many fractures, there's too many little blocks, and we have to generalize. But we can. I think it's like that sketching the stackpole. If you can sketch it, you really can model it. And as soon as you can see the repeating pattern, then we can generalize. And we get into multi-scale modeling, make a little model, characterize it, generalize the results, and then go to the next scale up. And the key to all this REV stuff is all about, repeating patterns. If the same pattern repeats, you can catch it. And the nice thing about fractures, the mechanically driven things, they're nice. They follow the rules. They are following rules, and there will be a pattern. And it's just, I glibly say just a question of, but you can find the patterns. And as soon as you got the pattern, then you can phone Sebastian and he'll tell you the answer. In fact, Victoria diagnostics on it.
Hadi knows much more about embedded discrete fracture methods. He did his PhD on this. And
perfect. You know, your friend, take that email and get him to Hadi.
REVs, the question from Reza Nugraha, how do we define an REV in the context of point 4 of a good model element?
REV, well, it was the third thing. It was the scale thing. So REVs is in the number 3. It's in the scale thing. And then, yes, phone Hadi, because he's got a PhD on it. So it's all to do with the scale thing and knowing the scale of, once you've got the length scale of the heterogeneity, once you've got that, and you can sketch it or conceptualize it, then you can parameterize it, and then you're away. And there's a bunch of publications. If you want, I mean, anyone is welcome to email, by the way. I don't know if we give emails away, but I'm very happy to take emails. And then I'll post them onto Hadi and Neil. But there's references on this. And there's the chapter, Phil Ringrose, he wrote a chapter on this in the design book, with work from him and Shettle Nordahl, specifically matching it onto the world of reservoir modeling. And there's a number of very good articles before that. Tom Anzok has written about this as well, in the context of fractures. Hadi, what's your favorite reference, Hadi, on REVs and fractures? Apart from
really rather just let you advise. It's your talk.
Okay, Nordahl and Ringrose. Go for that one. Sebastian.
Question from Andreas Busch. Are machine learning, artificial intelligence already making a difference, or will they only be valuable tools in 5, 10 years or more from now?
Oh, a cheeky question, Andreas. Yeah, good question. I don't know. What do you think? I think they're taking a lot of time at the moment, because we're thinking about it for the first time, and there's probably a whole bunch of useless work being done but this is research, isn't it? We explore and we try things. I would hope we're coming down to a way of realizing when it's useful. And for what it's worth, and I ask opinion from others, because this is still a new subject for us. My feeling is it's there to help you interrogate data. I don't think it's there to find solutions. I think it's to find the structure inside your data. We're just looking for patterns, aren't we? We're just looking for patterns. And I think that's where I'm coming down to, having sat through a few conferences on it. In which case, we can do it now. And then we have to phone people from Amazon or Google and just say, right, what are you doing? And that, give us your algorithm, which they won't. And then start throwing it at big data sets. The hard thing is our data sets have to be clean, and it works for Google and Amazon because they're looking at orders and mechanical things like that. We're looking at we look at a high degree of imperfect information. And I think that's going to be the challenge for us, is do you throw an ML algorithm at imperfect data and hope for something? And I don't feel good about that. I've got a feeling we might be lining ourselves up for some disappointments. But in principle, we can use it now. If you've got clean enough data, yeah, tomorrow, I think would be the answer, Andreas, but you've got to have a clean data set. Have you got any thoughts, Andreas? And have a think, come back if you have. Or tell me when I'm in Edinburgh.
We have another question from Vinicius, and there's two related questions that I read one after. But you answer this one first, and I follow up with a related question. Vinicius asks, when it comes to uncertainty, should we focus more on uncertainties that are not exactly from the model, like velocity uncertainties, impact of GRV, instead of doing multiple porosity scenarios?
Oh, absolutely. I mean, one of the big flaws with modeling, and we've got a lot of models of channels, and yet not a small percentage of the world's reservoirs are made of channels. Most of it, as Sebastian knows, are actually made of limestone. So why do we make lots of models of channels? Well, it's because the modeling software is good at it. All the geostats textbooks, think how many of the examples are channels. It's almost a joke, really. Next time you pick up a geostats textbook, I bet they illustrate it with an example of channels. It won't be diagenesis in limestones. It'll be a channel. So we tend to be led by the things that the software is capable of doing, which is why carbonates fell out, diagenesis falls out, and then fractures for a long time. A lot of it was based around clastic sedimentology. So yes, absolutely, and that's why we go to the sketch first. Otherwise, we'll be led, we'll be anchored, we'll be primed by the software, and then anchored on what it can do. So start with the sketch, start with your pencils, and then think about how to model it. And that's why it was so important that we don't try and make models of what it really looks like down there, because it's too difficult. If we can drop that idea and just say, I've made a sketch, I now need to make a model representation. Let's remember what the word model means. It's not the real thing. It's a model. That's why we don't call it the real thing. We call it a model. We can make a model of a sketch. And it gives you the chance of getting really good pencils. Sorry, back in a minute. It's not over for GeoScience. We still get to use Caran d'Ache pencils. Switzerland, there we go. ETH, I know you take it. And look, you can get Paul Smith pencils. How about that? It's like £3.50 a pencil. So, you can still do the GeoScience stuff. Do the sketch and then make the model. Led by the sketch.
I promised a follow-up question, or a related question. So Olavina Sarako asks, what is your view about using 4D seismic images to update the simulation model, which just talked about velocity uncertainties or uncertainties in the data itself?
Fantastic. Yes, if you got it. It's data, isn't it? It's data. We would use all the data we can do. So absolutely, 4D imaging to update the model. Absolutely. And we could, Colin Macbeth, we can tie you up with Colin Macbeth at Edinburgh, at Heriot-Watt, using the the Edinburgh time-lapse project. And of course, others doing the same. Definitely, yeah.
I think Olarino did his PhD with Colin. I'm not sure, but he's definitely Heriot-Watt University. The question may be coming from.
Hello.
Nufali asked a really interesting question because it takes us back to the talk last week from Sally Benson on CO2 storage. So the question is, for CO2 storage modeling, heterogeneity is a favorable thing. Do we need to consider the lost heterogeneity, which complicates the simulation, or do we keep it simple and hence have a conservative model?
Okay, right. Well, Nufal, this is someone who's just finished a very excellent individual project at Heriot-Watt on the MSc program. And as I would expect, Nufal, an incisive question as always. No, with for example, your project for CO2 storage, in a difficult rock with lots of heterogeneity, no, you'd have to go in there. The example you're using had a lot of siltstones. It was one from down here in Wales. You got to get in there and work out what's going to happen with capillary pressures in that siltstone. This is all full ring rosette stuff. But once you've zoomed in and worked out what's happening on a small scale, then you can generalize and come back out again. So it's another REV thing. And you will aim for a simple representation, but try and capture the little bits of complexity in separate parcels. And that was this thing about not convolving everything together in one place. It's one of Richard Oxley's observations. With complicated models, it's just very hard to know what's going on. So it is, and Sebastian and Hadi, there is a scientific principle here, isn't there, that to solve a complicated problem, you don't make a complex model, you break it down into simple pieces. And once you understand the pieces, then you can put it back together. And there must be some great scientist of the past who has thought of
called Albert Einstein. That makes everything as simple as possible, but not simpler.
Oh, everything was very good. Yeah.
Well, simplification is not an easy job. It's sometimes easier to make it more complex. Sometimes.
Yeah, I go with that. We'll refer to Einstein from now on. There you go, Nufal, Einstein.
We do a question from Natalia Papatreka. Again, apologies if I mispronounce any names here. When we do facies modeling, which parameters do we need to consider as uncertain? Okay.
Well, I would do rock modeling, element modeling. So which might not, but I know what you mean. It's called facies modeling in the software. But which parameters do we need? Well, I'd bounce it back to you. I'd say I would look at the sketch. I would ask you to sketch the reservoir. I think any engineer who's working with a geoscientist, give them a blank sheet of paper, tell them to get their color pencils out because that'll make them quite happy, and then just tell them to sketch it and put a scale on it. If they can't sketch it, get yourself another geoscientist. But once you've got the sketch and the scale, then ask them which bit of that sketch are you certain about, or more certain about, and which one are you actually guessing? And I think the answer to your question is the answer to that question. And it gets us into the world of multiple sketching. So don't just do it once because it's your favorite sketch. Make multiple sketches and don't vary everything, but vary the things which you think the fluid would be sensitive to. So once you've done the pencil bit, then talk petroleum engineering. And remember that it's not a geological model. It's a flow model. It's a physical model. Florian would often say, it's about the physics of the subsurface. It's not really about, it's to do with geology, but this is actually about physics, really.
We have one final question, and I think it's a really nice question to close at excellent talk of yours, Mark. Shamil Kazanov says, thanks a lot for such a great presentation. What do you think can bring geological modeling to the next level? Is mathematics, advanced geological evaluation, or all together? So what's the future?
Well, I hope it doesn't depend on making geologists highly mathematical. Otherwise, we're all in big trouble, guys. I think the next step is looking back at the workflow. And I'm going to go back to something that Matt Jackson said. In fact, Sebastian was there 2 years ago, EAG at Paris. And I'd given a talk about stuff with REVs and things. And Matt made the very astute comment. He said, but we've known about this for years. Why aren't we doing it? And the answer was, we've not really addressed our workflows. I think we've got the tools and I think we have the concepts. If you just look at the work that's been done in Delft and Heriot-Watt and Imperial and then Stanford in ETH, loads of work has been done. Our problem is not adopting it. And I think I sort of see that as that's the little contribution. Hopefully, I'm trying to make through Heriot-Watt. I'm not going to be an Albert Einstein, because that's been done already anyway. But I would hope it's to make that link between a shed load of work that's been done, but it hasn't been fully applied. And I think that's where you can make some enormous gains by just detaching from the standard workflow given by the software and thinking through the design yourself. So I'd like to think the next step is design, enlightened design.
On that note, thank you very much, Mark. Apologies for any questions. There's still questions coming through that we haven't answered, but Mark kindly offered to receive emails, and you can find his email on the Heriot-Watt University webpage. So thank you for an excellent talk, Mark. Thank you, everyone, for plenty of questions. Again, as many comments, thanking you from your audience, and thanking you for the talk. So with that, I hand over to Hadi for some final comments before we close today's webinar.
Thanks, everyone. Mark, once more, thanks a lot. I would like to announce that our next week's speaker is Professor Felle Knude from Ghent University in Belgium. Felle will talk about porous scale processes and imaging, micro scale processes in the subsurface formation or porous media in general. Until next week, stay happy, healthy, and tuned. And we all see you next week, again, the same time, Thursdays, 4 p.m. Central European and 3 p.m. in the UK. All the best.
Thank you for having me.
Thank you.